All right, we are in the third part of learning Rust series, I think. Let me see here. Yep, this is part 3. And let's see what's here. Common programming concepts. Appear in almost every programming language. How they work in Rust. Many programming languages have much in common. By this, probably they mean C family languages. Have much in common at their core. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust. Explain conventions. Learn about variables, basic types, functions, comments, and control flow. These foundations will be in every Rust program, and learning them early will give you a strong core to start from. Right, so this is not a declarative language, obviously. So you have all of these constructs. Rust language has a set of keywords that are reserved. Okay, yeah. You can't use them as names of variables or functions, which is expected. Guess these are the keywords. Quite a few of them, actually. All right. And most of the keywords have special meanings. You'll be using them to do various tasks in your Rust programs. No current functionality associated with... Really? Interesting. They've been reserved for functionality that might be added in the future. Interesting. So this is, I guess this is an important thing for backwards compatibility, ensuring it in languages. Interesting stuff. And these are the reserved ones. Wow. All right, so variables and mutability. As mentioned in storing values with variables, section by default. Where is that section? Oh, right there, under programming guessing game. By default, variables are immutable. This is one of the many nudges Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. Okay. However, you still have the option to make your variables mutable using the mute keyword, I think. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, once a value is bound to a name, you can't change that value. To illustrate this, generate a new project called variables in your projects directory by using cargo new variables. All right, let's get our PowerShell. This is another program, by the way. You install this separately. If you have a Windows machine, just type PowerShell into Google, and you can download this from Microsoft. Let's go to D, CD code. That's where my code resides. Rust and project. Is it? Yeah. Okay. So we are going to do cargo new variables. Cargo new variables. All right. So I got it. Then in your new variables directory, open main.rs and replace its code with the following code. Okay, let's go to our VS Code here, code editor, and go to not guessing game this time, variables, source, main.rs. Can I save this? I think this is saved. Why does it say M? What does that mean? Modified. Okay, save it. All right, main.rs. Let's do let x assignment 5 print line macro. The value of x is x. And then assign something else to it. And then practice again. Okay, cool. Save and run program using cargo run. All right, let's do that. Cargo, oh, I gotta go to CD variables and then cargo run. All right, I got the same error message here. This example shows how the compiler helps you find errors in your programs. Let's do this. Compilers can be frustrating, but really they only mean your program isn't safely doing what you want it to do yet. So errors are good for programmers. You guys should know if there's a question about that. They do not mean that you're not a good programmer. Experienced rustaceans will still get compiler errors. You receive the error message, cannot assign twice to immutable variable x because you tried to assign a second value to the immutable x variable. It's important that we get compile time errors when we attempt to change a value that's designated as immutable, because this very situation can lead to bugs, race conditions and such with concurrency, I think. If one part of our code operates on the assumption that a value will never change and another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to do. Yeah. The cause of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. The Rust compiler, yeah, so you might even not be able to reproduce that bug. The Rust compiler guarantees that when you state that a value won't change, it really won't change. So you don't have to keep track of it yourself. Your code is thus easier to reason through. But immutability can be very useful. Let's see the code again, by the way, if you're wondering. Let's do this. There we go. Immutability, but mutability can be very useful and can make code more convenient to write. While the variables are immutable by default, you can make them mutable by adding the mute keyword in front of the variable name, as you did in chapter 2. Go see part 2 if you haven't seen that. We did that over there. Adding mute also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. So mute actually makes a variable because its value can vary now. Otherwise, all you have are constants. For example, let's change source main rs to the following. What are we doing? Let mute. Okay, just add a mute here. And when we run the program now, let's run it. There we go, run. And now it works. All right. We are allowed to change the value bound to x from 5 to 6 when mute is used. Ultimately, deciding whether to use mutability or not is up to you and depends on what you think is clearest in that particular situation. Now, they have constants. Interestingly, they have immutable variables. They also have constants, interestingly. Constants are values that are bound to a name and are not allowed to change, but there are a few differences between constants and variables. First, you aren't allowed to use mute with constants. Constants aren't just immutable by default, they're always immutable. Interesting. Okay, so constants are like double constants, and variables in Rust are constants, but constants in Rust are like double strength constants, I guess. They're always immutable. You declare constants using the const keyword instead of the let keyword, and the type of the value must be annotated. Okay. So you would probably use const throughout, right? If you want your variables to be immutable. Why would you not use const all the time? If you're not considering your changing your variables. All right, maybe we'll get the answer to that. And the type of the value must be annotated. Okay, so the type must be annotated. We'll cover types and type annotations in the next section, data types, so don't worry about it. Just know that you must always annotate the type. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code may need to know about. The last difference is that constants may be set only to a constant expression, not the result of a value that could only be computed at runtime. Oh, okay, so you can't use const everywhere then. I see. Here's an example of a constant declaration. And uppercase letters are, I guess, the convention here for constants in Rust. Const 3 hours and seconds. You have a colon there, and an unsigned 32-bit integer, and a mathematical operation. Constant's name is that, and its value is set to the result of multiplying those things. Rust's naming convention for constants is to use all uppercase with underscores between words. The compiler is able to evaluate a limited set of operations at compile time, which lets us choose to write out this value in a way that's easier to understand and verify, rather than setting this constant to the value of 10,800. See the Rust references section on constant evaluation for more information. Shall we do that? Constant evaluation. Constant evaluation is the process. That's chapter 17. Yes, we're going to look at that later. Const context, const functions. Computing result of expressions during compilation. Only a subset of all expressions can be evaluated at compile time. Certain forms of expressions called constant expressions can be evaluated at compile time in const contexts. These are the only allowed expressions and are always evaluated at compile time. In other places, such as let statements, constant expressions may be, but are not guaranteed to be, evaluated at compile time. Interesting. Behaviors such as out of bounds, array indexing, or overflow are compiler errors. Its value must be evaluated at compile time in const context. Otherwise, these behaviors are warnings, but will likely panic at runtime. So your program is going to crash, I think. Following expressions are constant expressions, so long as any operands are also constant expressions and do not cause any drop calls to be run. I don't know what that is. Literals, of course. Const parameters. Okay. Pass the functions and constants. Cursively defined constants is not allowed. Pass the statics, whatever that is. Tuples, arrays, structs, block expressions, including unsafe blocks. Let statements and thus irrefutable patterns, including mutable bindings. Assignment, compound assignment, expression statements. I don't know what most of these are. Okay, so we're going to come to this later. All right, for more information, okay. Constants are valid for the entire time a program runs within the scope in which they were declared. This property makes constants useful for values in your application domain that multiple parts of the program might need to know about, such as the maximum number of points any player of a game is allowed to earn, or the speed of light. Okay, naming hard-coded values used throughout your program as constants is useful in conveying the meaning of that value to future maintainers of the code. It also helps to have only one place in your code you would need to change the hard-coded value needed to be updated in the future. Interesting. Shadowing. As you saw in the guessing game tutorial in chapter 2, you can declare a new variable with the same name as a previous variable. Rustaceans say that the first variable is shadowed by the second. And this is also a commonly used term in other programming languages. Which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any uses of the variable name to itself until either it itself is shadowed or the scope ends. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. Okay, so that's shadowing. Let's do that. So you don't need to mute this. You can say let x 5 and then let x assignment operator x plus 1. Okay, let me just type the code as it is here. And then we're creating a block. And inside the block, you got let x times 2. And print something in the block. The value of x in the inner scope is of x in the inner scope is x. And then again, the value of x is x in the outer scope. All right, so let's run that, see what happens. Gotta go run. The value of x in the inner scope is 12. The value of x is 6 in the outer scope, that is, which is, I guess, expected. So it starts as 5, it becomes 6 here, and then it doubles inside the block, but outside the block, when the block is done, this variable is discarded, probably. And then outside the block, you got the old value here. Program first binds x to a value of 5, then it increases. It creates a new variable x by repeating let x, taking the original value and adding 1. So the value of x is then 6. So you don't need to make the x variable mutable to do this, right? You can just shadow it. This probably copies, creates a copy of x, or creates a copy of this object in another place in memory and gets x pointing to that object. One to the value of x is then 6. Okay, then within an inner scope created with the curly brackets, the third let statement also shadows x and creates a new variable, multiplying the previous value by 2 to give x a value of 12. Okay, so this is how you actually do variables in Rust, right? You use shadowing. Mute is probably for specialized cases only. You copy everything everywhere. You create a copy of everything everywhere. So, or something like that. Use a new location in memory. Even though you use the same identifier, after this operation, this identifier, the same identifier as the one before here, starts pointing to the new object that's created, is my guess. When that scope is over, the inner shadowing ends and x returns to being 6. When we run this program, it will output the following. Yep. So this x is only valid inside this block, curly braces, right? When this block ends, so does this version of x, this identifier x. The parent identifier here, this x, though, still lives on after this block is done. Shadowing is different from marking a variable as mute because we'll get a compile time error if we accidentally try to reassign to this variable without using the let keyword. By using let, we can perform a few transformations on a value, but have the variable be immutable after those transformations have been completed. Okay. The other difference between mute and shadowing is that because we're effectively creating a new variable, when we use let keyword again, we can change the type of the value, but reuse the same name. Interesting. For example, say our program asks a user to show how many spaces they want between some text by inputting space characters. And then we want to store that input as a number. Okay, the first spaces variable is a string type, and the second spaces variable is a number type. Yeah. Shadowing thus spares us from having to come up with different names such as spaces string and spaces num. Instead, we can reuse the simpler spaces name. However, if we try to use mute for this, you're going to get an error because they're not of the same type, right? The error says we're not allowed to mutate a variable's type. Error mismatched types. Expected due to this value, expected string, found usize. Now that we've explored how variables work, let's look at more data types they can have. All right, so we are going to continue on in the next part with data types.